So Cramer's rule was discovered by this guy here. His name is Gabriel Cramer. If you look at his Wikipedia page, it will show you that he actually got his doctorate, so his PhD, at the age of 18. So some of you guys are 18 years old. He had his doctorate at 18.
Sounds like a parent.
Huh?
Sounds like a parent.
I am a parent.
This kid did this.
I have three kids. Yeah. So anyhow, yeah, he was really smart. 18, he got his doctorate, and at age 20, he was the co-chair of the mathematics department at the University of Geneva, which isn't. I think it's in Switzerland. So anyhow, he was very smart. Obviously, he died pretty early. I think in his early 40s, health problems. But he came up with Cramer's rule, a bunch of other things, but the main thing that he came up with is Cramer's rule, and you can see some other things: Cramer's theorem, Cramer's paradox. He's basically named everything after himself, which I don't blame him. Yeah, probably named it after myself too. Remember, Sue came up with it, right? If you think of Isaac Newton, he named his laws of physics after himself too. So Cramer's rule because this guy discovered it. What's that?
It's not legacy.
Right. Now you know. All right. So one question that you might have had so far is, why are matrices useful? Well, there's a lot of different uses. One of them is what we're going to look at today, and we're going to be solving some systems of equations using matrices. You don't have to write down these equations right now, but a way that we can solve a system of linear equations. You've seen these before in your math life. There's a lot of different real-world variables you could plug in for these and make them bigger as well, and you can solve them using matrices. So we're going to start with some basic ones today. These are both systems of equations that you could solve, probably just with tools that you already have. For instance, I want you to take a second and see if you could solve this. So try to solve this, just using some knowledge that you might already have, to solve for x and y. Let's see what you guys can come up with. Yeah, you can. Take a minute, type in your answer when you think you got it. 4 and 4 doesn't work. It works for the first one, but not for the second one. Six and 2. So if you got 6 and 2, that would be correct. There's several ways you could figure that out. One would be just maybe looking at it. You also, back in 7th grade, learned some different ways of solving this. There was substitution, elimination. You could also graph these. You guys remember doing those methods? Substitution, elimination. Elimination would be where you add or subtract these. So let's say you subtract these two equations. The x's would cancel. This would turn into a plus, so you get 2y equals 4, and then y equals 2. Remember doing that? Or substitution would be if you solve for one as variable, so if you solve for x, x would be 8 minus y, and then you take this and you plug it in for that x and solve it. Remember those methods? Okay, so those are valid ways to solve this. You could do the same with this one. This one would just be a little bit harder. You'd have to, if you wanted this eliminate, you'd have to multiply this equation or this equation by something. And it would be a little harder to do this one. And as you get harder and harder, these methods, they still will work, but they become a little bit more confusing. And so one way that we could solve these is using something called Cramer's rule, which is a way of using matrices to solve systems of equations. So that's what we're going to do today. In order to do Cramer's rule, we need something called a determinant. Determinant is just a number that's used in Cramer's rule. We need to figure out how to do this first. So a determinant, it's a scalar value. What does scalar mean? Like when it's scalar multiplication, what is that? What's the difference between scalar multiplication and matrix multiplication? You know? What's a scalar? A scalar is just a single number. So like that first one we did on the quizzes, it was 3 times the matrix. That was scalar multiplication, just a number times the matrix. So a determinant is end up just going to be a single number, and we get it from a square matrix. A square matrix means it has the same number of rows as columns. So like a 2 by 2, 3 by 3, you could do a 4 by 4, etc. Those are square matrices, 5 by 5. So this number can only be computed with a square matrix. Today we're just going to do a 2 by 2. Monday we'll probably look at a 3 by 3. It gets a little bit more complicated. Today we're just going to focus on 2 by 2 determinants. So there's a little formula that we use. Looks like this. We're going to use these bars that look kind of like absolute value bars. And I'm going to put some letters in here, but we'll change them into numbers here shortly. So I'm just going to call this matrix the elements A, B, C, and D. And this is the notation we use for a determinant. We just put these big vertical bars and like absolute value bars. And to find the determinant, we're just going to do some cross multiplying. So we're going to do A times D minus B times C. A times D minus B times C. So multiply these and then subtract when you multiply those. AB minus BC. That's it. So let's put some numbers in here. This as an example. Try it. So I'll say 3, 5, -1, and 7. And we're going to find that determinant. So what we're going to do is multiply across here. It's just important that you do the right order. So we always start with the one on the top left. 3 times 7 minus 5 times -1. And we'll do this enough times that you just memorize this formula. It's not hard to memorize, and you do it a lot in Cramer's rules, so you'll memorize it. 3 times 7 is 21. -5 and -1 is +5. So the determinant of this is 26. So just a single number at the end. It's a scalar value. So thus far, we haven't actually seen why this is helpful, but you have to know how to do a determinant in order to do Cramer's rule. If you do a 3 by 3 matrix, it gets more challenging. So we'll do that on Monday, but 2 by 2 is pretty easy, pretty straightforward. Right. So next is Cramer's rule, which is where we're actually going to use these determinants. So Cramer's rule, if you don't want to write down the whole definition, that's fine. Just make sure you're going to get that formula here. But basically, it's a way that we can solve a linear system of equations. The only thing is there has to be the same number of variables as there are equations. So what that means, this part, we could solve a system of 2 equations, but we need 2 variables. So they have to have an x and a y. We need 2 equations. If we're going to do 3 equations, then we need 3 variables. So we need like x, y, and z. You can do 4 equations. You would just need 4 variables. So on and so forth. You always have to have the same number of variables as you do equations, which is generally the case. And you're going to want to write down this formula. It's going to look confusing, But when we actually use it, I promise it isn't that hard to use. So it will look confusing at first. So this is the most important part of algebra. So we're going to say given, we'll be given a system of equations like this. We're going to say ax plus by equals s. S is just a constant. And then our second equation, we're going to call cx plus dy equals, and what variable you think we use there? This was log 1. Why S and G are chosen, I'm not really sure why, but for whatever reason, Gabriel Cramer decided that those were the best variables to choose there. S and T. One reason why might be is if you have like say like a 5 variable, 5 system of equations, you would have to use a lot more of these. So you would do like A, B, C, and D up here, E, F, G, and H. And these are far enough down the alphabet that you would never use them like if you were doing like a 5 by 5 system. Well, because those are typical variables that they use. And W and Z. So if you had like a 4 variable 4 system, it would probably look like this: ax plus by, and then you would do cz. But if you had 4 variables, typically the most is 3. So you would use these variables: ax plus by plus cz, and then you could have dx plus ey plus fz, and these are far enough that they wouldn't get used. Right. So I think that's why those are chosen. But S and T, those are just these are going to be numbers. So the A and the X, the B and the D, and the S and the T, those are all just going to be numbers. So it looks confusing right now, but it'll be less confusing when there's numbers there. All right, so that's this is just what we're going to be given. Now to solve for X, it's going to look like this. X equals the determinant of ST and BD over the determinant of our ABCD. And another way that we're going to write this is D sub X over D. And this is how we solve for X. Now again, I know that looks confusing right now, but I'll explain to you what's going on here. So the bottom of this fraction, this determinant of A, B, C, D, is just the determinant of the numbers in front of the variables. So whatever numbers are in front of the variables, we just do a 2 by 2 determinant of that. Now this top one, notice the B and the D come from the Y's, but we're solving for X, and if you'll notice that the X column here, instead of having A and C, it's been replaced by the S and the T. So since we're solving for X, we actually like swap out the X for the sort of the answers. Those take the place of the X's. And then the Y is really similar. When we solve for Y, it's going to be determinant, and we're going to have A and C in there. But when we're solving for Y, we're going to take out B and D, because those are the Y coefficients, and we're going to swap them with S and T. So we swap out the Y's, and then it's going to be over, and then the same determinant, A, B, C, D. So in the X's, we swap out the X's, and in the Y's, we swap out the Y's. This is also written as D sub Y over D. So this is the formula here. Probably thinking like, well, where's the numbers, right? Well, So come in and we'll do a problem. Now, when we do a problem, it'll all come together. So let's go ahead and try one here. Does everyone go with formulas? Good. Okay. We'll leave the formula there for just a second. So we'll start with a nice easy one here. Most of these are going to be ones. And this is actually the one that we solved to begin with. So I'm just going to kind of show you how it works. And we should get the same answer we did when we solved it to begin with, which was that 6 and 2. All right, so there's our system of equations. The first thing that we're going to do is we're going to find three determinants. We need a d sub x, we need just a regular d, and we need a d sub y. So that's what we're going to do first. We're just going to calculate those three determinants. I always do just the d first. That's what we're going to do. We're going to do d equals. And then the d is a, b, c, d. So it's just going to be the numbers in front here. These it's a really easy one, so these are all ones. This is 1, this is 1, this is a 1. This is a negative 1. But that's with the a, b, c, and d there. There's no numbers, which means there's an invisible 1 there. So it's going to be the determinant of 1, 1, 1, and negative 1. So that's going to be our first determinant. Just take the coefficients of the x and the y's. This equals, we just do a times b, so 1 times negative 1, minus 1 times 1. So that becomes negative 1 minus 1 is negative 2. Everybody with me so far? A lot of 1s, I know. All right, the next thing we're going to do is get d sub x. D sub x is going to be another determinant. But remember with the x's, we're going to swap out the x values. So we're going to swap out these two 1s with the answers over here, 8 and 4. So it's going to be 8, 4, and then we're going to keep the y coefficients, 1 and negative 1. When we do x's, we swap out the x column. And then we're just going to do another determinant. So 8 times negative 1 minus 1 times 4. So this becomes negative 8 minus 4, which is negative 12. All right, then we need one more determinant. This time it's going to be d sub y. So d sub y, we're going to keep the x's this time. So we're going to keep 1 and 1. And we're going to swap out the y's, 1 and negative 1, with 8 and 4. The x and the t. That's determinant. So we do 1 times 4 minus 8 times 1. We'll get 4 minus 8, which is negative 4. So we compute three determinant values. All right, now our formulas, x is d sub x over d, which is the same thing as just saying d sub x this over d here. So x is just going to be negative 12 over our d, which is negative 2. Negative 12 divided by negative 2 is positive 6. And y is going to be d sub y over d. D sub y was -4, and d was -2. -4 divided by -2 is 2. So then our answer, we want to write as a coordinate pair, 6, 2. And that was the same answer we got before. Now granted, this seems more complicated, but it works for any system of equations, especially ones that are difficult to solve. And I promise it goes faster too the more that you do it. All right, here we go with that. Try just a little bit harder one. This one that's got some more numbers here. So you can see this one will be a little bit harder if we try to do like elimination or substitution or something like that. Would be more challenging. So we're going to do 3 determinants always to start. We're going to do our d sub x, and our d sub y. Let's start with d. For d, we're just going to take the 4 coefficients here. So we have 5, 2, -1, and 3. And then it's just quick. Once you do several determinants, you can do most of it in your head. Just do 5 times 3 when that was 15, minus -1 times 2 is -2. So you can skip that for a second. And then that becomes plus 2, so it's 17. And then we do d sub x. For d sub x, we are going to swap out the x values. So we're going to swap 5 and 2 with these answers, 13 and 12. 13, 12, keep the y's, -1 and 3. So for x, swap the x's. Same process here. 13 times 3 is 39. Minus 12 times -1 is -12. So it becomes 39 plus 12, which is 50. And then one more. We'll do d sub y. So d sub y, we're going to swap the y's with the answers. Keep the 5 and the 2. We'll swap the y's with 13 and 12. Then we're going to do 5 times 12, which is 60. 13 times 2 is 26. 16 minus 26 is 34. Now, last step is going to be to write these as our fractions there. So x is going to be d sub x over d, 51 over 17. So that's going to be, you know that? 17 go to 51. 3 times, yep. 17, 34, 51. And y is going to be 34 over 17, which is 2. So our answer then is 3, 2. And you can do a really easy check for your answer as well. Just plug them into these two equations. So 3 and 2, 5 times 3 is 15, minus 2 is 13. So that's good. 2 times 3 is 6, plus 3 times 2 is 6. 6 plus 6 is 12. Okay. And you see that actually was pretty fast, right? Once we know what we're doing, just computing those determinants real quick. And it really is pretty quick. So it seems long at first, seems like there's a lot going on, but it really is pretty quick. I want to show you a couple things real quick here, and then you don't have to write this down, but I do want to show you a couple things. Don't write this one down. But on your assignment, I don't think there's any like this, but I want to show it to you just so you're aware. Notice how this top one doesn't have a y value, right? So how many y's are there? Right, 0y. So if you just see this, think of this as like 3x plus 0y. You still have to put a 0 in there. Just be aware of that. That one will be really easy to solve though without Cramer's rule because you just divide by 3 on the top. And then I want to show you one other one, this one really quick. We should have time to do this one. We don't actually have to do the entire thing. So okay. So let's go ahead and set up and solve for D to begin with. So D is just going to take the 4 coefficients here. 3, 2. And take a second, go ahead and calculate D real quick. You'll get negative 12 minus negative 12. Negative 12 plus 12. Should have gotten 0, is that right? Mm-hmm. So let's think about what's going to happen. We're going to get some sort of d sub x is going to be a number, right? It's going to be over 0 for x, right? And then y is going to be the same thing, some number over 0. So is this possible? This one's not possible. There's actually no solution to this one. Because both of the answers would be undefined, right? They both have a 0 in top. So there's no solution. And the reason why, if you look at this, notice how if I were to just like multiply this top one by 2, then it would be 6x minus 4y equals 8. So they're actually the same equation, except the answer is different. So how could 6x minus 4y equal 8 here, and 6x minus 4y equal 0 there? There'd be no way that no two numbers would make that equal. So that's why there's no solution. If there was a scenario where they were the same exact equation, so if this ended up giving you 0 instead, then there'd be infinite solutions because any number you plugged in would work. If they were exact same equation, so you could make them exactly the same. It'd be infinite solutions. All right. Just got a few minutes left here. I want to give you just a heads up of what you're going to be doing tomorrow. So tomorrow you're going to have an assignment over this. It's going to be on Delta Math. I just want to pull it up real quick and show you what's going to happen here. I'm also going to just post a short video just doing a couple of these examples to refresh your memory. But what you have to do here, you have to use Cramer's rule, and it says you have to write the 3 determinants in. So those, you have the d sub x, d sub y. You're just going to type those 3 numbers in. It doesn't matter the order that you do that. And then you're going to put in the answers there. If they would happen to be a fraction, make sure you put them in simplest form. So if it's a fraction, make sure you use simplest form. But that's going to be your assignment for tomorrow. I'll post that. This will be available at midnight tonight if you want to. Someone wanted to stay up really late and work on it at midnight tonight, so I posted that.